We've made it! We're finally ready to break down real circuits that have both series and parallel. And I'm going to promise you guys something. If you do it the way that I do it, it's not going to be hard. Each of these problems is going to take a little bit longer than it used to, and I do it a little bit differently than the book to make it simpler. But if you follow my procedure, I promise you this is not going to be hard. This is also the last exam. Last exam? No. This is the last lecture before our next exam. And so after this point, we've covered 2/3 of the entire course. We are wrapping up the section on how to break down circuits. And so before we jump right in, I'm going to do most of this inside of just writing on the board as opposed to using PowerPoint. And before we get there, we need to talk about how to identify a series parallel circuit. And so if we look at this, the first thing we need to ask ourselves, is this circuit in series? And, well, we would do what we normally do, right? We could start here and trace it with our finger. So R1 is definitely in series, but notice at this point I have a choice. And so I know this can't be a purely series circuit because if it were, we wouldn't have any choices. But I can also say it's not totally in parallel, right? Because the top of this and the bottom of this aren't the same as the top of this and the bottom of this. So what we need to do is we need to identify which parts are in parallel and which parts are in series. And if I look at this, right, we can see, I think pretty easily that the top of this and the top of this is the same. The bottom of this and the bottom of this is the same. And so R2 and R3 are in parallel. And so I could say R2 is in parallel with R3. But then if I think of this as one whole thing, well then R1 is in series with those two in parallel. And so I'm not going to make you do this much, but we could write that out like this. And that's what the book is trying to teach you at that point. Okay, let's try another one. If I look at this circuit, again, we can try to trace it, and we would see that, well, if I start here, the source is in series with R1, but then again, we have a choice to make. And since I have a choice, we can't be series totally. If I look at that choice, though, I can see that the top of R2 is the same as the top of R3, and the bottom of R2 is the same as the bottom of R3. So these two I can see are in parallel. So I can again write that R2 is in parallel with R3. Now if we picture this as one whole device, right, then I can see that R1 is in series with that whole device, which is in series with R4. And so that's why your book would say R1 is in series with that parallel stuff, which is in series with R4. The book uses plus where they're in series, because remember we add up resistors if they're in series, and it uses that parallel notation with the double bars when they're in parallel. Most complicated one so far. Now, this one's really confusing to look at, and so I'm going to do this a couple times when we cover circuits this lecture. If a circuit is confusing, you're always free to redraw it. So let's try to redraw this one. The way that we redraw it is we want to start from the source. So I'm going to draw that source right here. So that's our VS. Now, it's hard to do on the screen, but what you want to do in real life is trace it with your finger. So I would start here. And notice I immediately have to run into R1. So I'm going to draw that, and I immediately have to go into R1. After I hit R1, I keep going, and notice I immediately have a choice. And so what I want to do is I want to write that, even before I write anything else, that choice on my screen. So notice I could go this way or this way. If I go if I make a right turn, so if I go this way, I immediately run into R2. If I go the other way, I immediately run into R3. At this point, notice that these two, the bottoms of these two resistors, connect up to each other again. So I'm going to draw that. I'm going to draw them connecting up to each other again. After this point, right, so it's again connected. After this point, we can go again two different ways. I can go this way, or I can go this way. So I again want to draw that. I can go one way or another. If I go on the left side here, I run into R4. So I run into R4. If I go to the right, I run into R5. If I go the other way, I run into R5. After that point, notice again they come back together and go to one wire. And they come back. So they come back together, they go to one wire, and then if we continue, it goes back to the source. So this I think is pretty confusing, this first circuit, to figure out what's in series and what's in parallel. But if we look and we redraw it, I think this one's much easier to see, right? I think it's pretty easy to see that the tops of these two, so here and here, are the same. The bottoms are the same. Tops are the same. The bottoms are the same. And so if we did this one, right, we start from here. We have to run into R1. Then after R1, we have R2 in parallel with R3. And then after that, we have R4 in parallel with R5. And so I think it's much easier to do after we've redrawn it. I don't want this notation to confuse you very much. Like I said, we're not going to use this, but I was just trying to give you some idea of what the book is doing in that section and how they're comparing these things. So the only takeaway you really need to get from what we've covered so far is being able to see what is in parallel and what is in series. Okay, so here's how we're going to break down the big circuits. I know it's going to look like a lot at first, but we're going to do a bunch of examples, and I promise you it's not bad. The first thing we need to do is step 1. We need to identify parts that are either in parallel or parts that are in series. Okay, so they have to be in perfect parallel or perfect series. Once we found a part that's in perfect parallel or perfect series, what we want to do is we want to redraw the whole circuit, but replace those parts with their equivalent resistance. Let me show you what I mean. So what I mean is, remember, if we have two resistors that are in parallel, like this, they have the same tops and the same bottoms, remember we can calculate what the total resistance of that part is. And so let's do this example, right? If I had a 2K and a 6K in parallel, I'll open my calculator here. We use the same formula we used last week. So we would have 2e to the 3. We'd hit our 1 over x button, plus 6e to the 3, hit our 1 over x button, equals 1 over x. And so notice that those two in parallel are the same as one resistor that's 1500. And so that would be the same as this right here. Or a 1.5K. So this here is literally exactly the same as that. And so I'm going to replace it with that in my circuit. And if we're looking at a series one, remember if they're in series, we just add them up. And so this 1K and 3K in series is exactly the same as just one resistor, that is 4K. And so that's what I mean when we want to redraw it with its equivalent resistance. Now what we want to do in step 3 is just keep doing step 1 and step 2 over again, shrinking the circuit smaller and smaller. The only rule we have is we can only do parallel or we can only do series. We can't do parallel and series at the same time. Even if you're smart enough to do it in your head, don't, because then we'll be missing stuff when we work back. The last step is we want to work back through all the drawings we did, solving for every current and solving for every voltage. I'm sure you're freaking out. I know you're freaking out. I can hear you through the internet. You're freaking out. It's not going to be that bad. Let's just start doing some examples. So I've got one right here. Now, what I wanted to show you is your book likes, for some reason, giving you problems like this, where notice they have 3 separate grounds. Let me switch color because I'm all white. Notice this has 3 separate grounds. Don't let that confuse you. Remember that all grounds are connected. And so if it helps you visualize it better, you can just ignore those grounds and pretend like there's a wire going across here. It's exactly the same as if I had a wire going across all that. So now let's go ahead and follow our steps. First thing I need to do is I need to identify, is there anything in perfect series or in perfect parallel? Well, this 1K up at the top isn't in series with anything, because if I trace it, notice it has 2 choices to make. But this 2.2 and 3.3K, they're in perfect parallel, right? They share the same top and they share the same bottom. And so remember, what we want to do now is we want to redraw this whole circuit, but we want to replace them with their equivalent resistance. And so what I'll do is I'll do that right here. So I'm going to have a voltage source, 22 volts. Again, then we come from this and we run into our 1K resistor. After the 1K resistor, now I want to replace this parallel right here with its equivalent resistance. And so I draw just one resistor. We got to get the value for it, so I'm going to use our formula, right? I'll write it down one more time so we know what's going on. In this case, our equivalent is going to be 1 over the 2.2K plus 1 over the 3.3K. And so again, I'll pull up my calculator. That's not my calculator. And so we have 2.2 e to the 3, 1 over x, plus 3.3 e to the 3, 1 over x, equals 1 over x. And so we get 1,320. And so that's the same as 1.32K. So now, what you need to know is this circuit here is identical to this circuit. They're the same because we replaced those two in parallel with what their actual equivalent resistance would be. So far, so good? Not too bad, right? Now we need to look at the circuit again and see, are there any perfect series or any perfect parallel? Well, if I trace this, right, notice that if I go through this 1K, I then go directly. There's no longer any choice to the 1.32K. So those two are in perfect series. And so now what I want to do is, again, I want to redraw this circuit, a little arrow, and I'm going to replace those by their equivalent resistance. And so remember, if we have two resistors in perfect series, we just add up to get their resistance. And so 1K plus 1.32K would be 2.32K. And that's it. Because again, remember that if I have two resistors like this, 1K and 1.32K, that's exactly the same as one resistor that has 2.32K. Alright, now we want to look at it. Is there anything in series or is there anything in parallel? Well, we can't, right? There's only one resistor. We're done breaking it down. At this point, we can't break it down any further because there's only one resistor. Now's when we want to switch modes. What we want to do is we want to start from the one we broke it down to, and we want to solve for every voltage and every current. It's important that we get both. So first thing I want to do is look, do we know every voltage? Well, we do, right? Because we know that the voltage source is 22 volts. Since this is the only resistor, it must also be 22 volts. So there's nothing to solve for there. Do we know the current? We don't know the current, right? And so to solve for the current, I know that I've got my I of t here. We've got one resistor. Remember, V is equal to I times R. So if I want to solve for I, that's the same as voltage divided by resistance. I have 22 volts across a 2.32K resistor. And so if I solve for that, again, I'll bring up my calculator. So I've got 22 volts divided by a 2.32 e to the 3 resistor. And we get 0.0948. So that's going to be 9. If we move it over by 3 places, that's 9.48 milliamps. And so I'm going to draw that on my circuit. I now know that I have a current going this way that is 9.48 milliamps. Now I know every voltage and every current in the circuit. There's nothing more that we can solve for. So I want to check this one off because I'm done with it and move back to the previous one. And I want to take all the information I learned. Well, what did I learn? I learned that the current going this way is 9.48 milliamps. Okay, so now what can we solve for in this new circuit? because it's a series circuit, we already know every current. What don't we know? Well, I don't know the voltage drop from here to here, and I don't know the voltage drop from here to here. So I need to solve for those two things. Remember, to solve for voltage, we just simply have V is equal to I times R. What's so nice about breaking down the circuit this way and working backwards is this and this are the most complicated formulas we will ever have to use, and calculating the resistance. Because it'll never be more than solving for one voltage or one current. And so let's get our voltages here. I've got 9.48 milliamps, so 9.48 e to the negative 3 times 1k times 1 E3, and so that gives me 9.48 volts. And so if I write that here, 9.48 volts. Now we need to get this one, again, because it's series, it has the same current. So I've got 9.48 e to the negative 3 times 1.32 e to the 3. I get 12.51 volts. So I have 12.51 volts. Now notice, we know every single current, we know every single voltage. And so I can check this one off. We're done with this, and now we want to take it back up here to the original. So remember, I know that the current coming this way is 9.48 milliamps. I know the voltage drop across this resistor is 9.48 volts. Now remember, these two here, this resistor here and this resistor here, they're the same as this one resistor. So I know the voltage drop, because they're in parallel, is the same across them, and its value is 12.51 volts. So now, what don't we know about this resistor, this circuit? Well, let's go to every device. For R1, I know the current through it, and I know the voltage across it. For R2, I know the voltage across it, it's 12.51, but I don't know the current through this path. Same thing with R3. I know the voltage across it, but I don't know the current through this path. And so I need to solve for it. Again, we're going to use our formula over here. We know the voltage and we know the resistance. So for that one, we have 12.51 volts divided by 2.2 e to the 3. And I get, again, if I move this over by 3 spots, 5.69 milliamps. So again, we've got 5.69 milliamps going down the first path. For the second one, we have 12.51 divided by 3.3 e to the 3. And in this case, we get, again, if we move this over by 3, 3.79 milliamps. 3.79 milliamps. And now look, we know every voltage and every current in this entire circuit now. Right? If I were to ask you, what's the voltage drop across R1? Well, we got it. It's 9.48 volts. Voltage drop across R2? It's 5.69. Nope, not 5.69. It's 12.51 volts. Voltage drop across R3 was the same. If I asked you for the current, I1, which is the same as I total, by the way, notice it's coming from the total, that's 9.48 milliamps. If I asked you for I2, that's 5.69 milliamps. I3, that's 3.79 milliamps. And so without using horrible big equations, just by breaking it down step by step and working back, we never had to do anything more than complicated than series by itself or parallel by itself. And again, at most, one equation. And so that's how you break these down. If I were to ask you, what is the voltage at A? Well, if we start at 22 and we drop by 9.48, then it's going to be equal to roughly 12.51. You guys ready to try another one? Wasn't too bad, right? Looks like a lot. Takes a long time. That's the only downside of this way, is I think it's pretty easy. I'm sure it's not easy right now when you're first looking at it, but it will become easy. But it takes a long time. We won't always do it this way. We'll have other ways in the future. Let's try another one. Okay, so let's try this one. And I gotta be honest with you, this even kind of confuses me. This is an ugly looking circuit, right? I'm not entirely sure what's in series and parallel. So what I'm gonna do is I'm gonna redraw it before I even shrink anything. Just redraw it so it looks more like the ones we've been working with. So to do that, I'm gonna start at my 1 volt. No questions right now. I'm going to start at my 1 volt. So I've got my 1 volt here. Sorry, whoever that was, I'll get back to you in just a few minutes. Again, if I go from there, I have to go into a 47. So I'll draw my 47. Then I have to go through a 27. At this point, we have a choice to make. I can go that way, or I can go that way. So before I even look to see what's there, I'm going to draw that out. I can go that way, or I can go that way. If I go down the left side here, I have to run into a 27, and then I have to run into another 27. If I go the other path, I have to run into a 47, and then notice they connect back up. Right? They connect back up at this point, and then they go back over to our source. So I don't know about you, but it's much easier for me to see what's in series and parallel in this version than it is the one up there. So I'm going to work from this. So let me just move this up, give myself a little bit of extra room since I redrew it. Okay. So now we need to identify what's in series and what's in parallel. We'll notice that we have nothing in direct parallel. Right? Because while these two here, let me write it real quick, these two do share the same top, they don't share the same bottom. Right? Because this is not the same as this. So let me erase that. There's no parallel. Notice these two are in series, and these two are in series. And so remember our rule. We could never do series and parallel at the same time. But we can collapse two series at the same time. There's nothing wrong with that. We just can't do series and parallel. So what I mean by that is I can't add these two up in my head and know that that's what, 54? And do 54 in parallel with 47. If I do that, when we work backwards to solve for the voltages, we'll be missing information. So what I'm going to do is I'm going to collapse these two and these two in one step because they're both series. And so let me redraw that. I'll draw it below. And so we have, let me stick to yellow. So we have 1 volt. And if I collapse that 47 and 27, we get what? Well, let's pull up our calculator. We have 47 plus 27, which is exactly the same as having one resistor that is 74 ohms. So I'll write 74. Then over here, I'm going to collapse those two on the left. And we said if we add up 27 plus 27, that's the same as 54. So I'll write 54 here. And then we have a 47 on the right. Not too bad. Alright, now we need to look. Do we have any series or parallel? The 74 is not in series because it has a choice. But the 54 and the 47 are in parallel. So we'll go ahead and collapse those. So I've got 1 volt. It runs into a 74. And then if we need to calculate what 54 and 47 are in parallel. So I've got 54, 1 over x, plus, what was it? 40, what did I say it was? 47, right there, what am I doing? 47, 1 over x, equals 1 over x. We get 25 point, what is that, 1? We'll do 25.1. 25.1. And now we can see that we have just 2 in series. And so finally we'll collapse those 2 in series and move this up. And so we've got 1 volt. And that's going to give me what? 99.1? We've got 74 plus 25.1 is 99.1. And that's it. Can't break it down anymore. That's as small as she goes. I didn't mention this before, but if the question asks you what's R total of the whole circuit, this method also solves for R total. That value there, once we've broken this whole thing down, that's our R total value. So now remember, we need to work backwards, solving for every voltage and every current. So I know every voltage here, but I don't know the current. So I need to solve for the current that's going this way. This current, by the way, is I total, the total current for the circuit. So we've got 1 resistor and it has 1 volt across it. So we'll go ahead and figure that out. Remember, voltage divided by resistance gives us current. So I've got 1 divided by 99.1, which gives me, it looks like 10.1 milliamps. We could just say 10 milliamps. So we've got 10 milliamps. And I'll do 10.1. 10.1 milliamps. Okay. Nothing else we can solve here. So the most important part is the check mark, because it feels good. I'm done with it. That's right. Move this back to here. I now know that I have 10.1 milliamps flowing through this circuit. These are both in series. So what we're missing is I don't know the voltage here, and I don't know the voltage here. So we bring up our calculator. I've got 10.1 e to the negative 3 times 74, which gives me 0.75. So we've got 0.75 volt drop there. Again, got to do the other one. So we have 10.1 e to the negative 3 times 25.1, which gives me 25.4. Nope, not 25.4. 0.25, right? Yeah, 0.25. And again, notice, we can kind of check our work as we're going through this. Notice that these two need to add up to our total of 1 volt. And remember, it might be a slight error because we've been rounding and things like that. That's okay, but in general, it should be close. So now we know every single voltage in this circuit. We know every single current in this circuit. That's right, check mark it off. Now we need to bring back what we learned to the previous circuit. So in this circuit, I know now, there we go. 10.1 milliamps. I know that the voltage drop from here to here is 0.75. I know that the voltage drop, remember these are in parallel, so they have the same voltage from here to here, is 0.25. So what don't we know? Well, I know the current and the voltage across the 74. I know the voltage across the 54 and the 47, but I don't know the current. So I need to solve for, let me write it real big. So I need to solve for the current going down that resistor and the current going down that resistor path. So again, just in case we forgot, remember I is equal to voltage divided by resistance. And so on the left side, we have 0.25 divided by 54. And we get, if we move this over 3, we get 4.63 milliamps. So we have 4.63 milliamps. And on the right hand side, we have 0.25 divided by 47. And that's going to give us 5.31 milliamps. 5.32 actually. 5.32 0.32 milliamps. Again, we don't want to do a lot of checking of our work. I mean, we want to do a lot of checking of work. We don't want to spend a lot of time, right? If I add this plus this, I'm getting something pretty close to 10.1, so that looks good. Because remember, the 10.1 is what comes here and splits up into those two. At this point, we know every voltage, every current, everything there is to know about this circuit. Check it off. Bring all of our information back up to the original circuit. I now know that from here to here, I have 10.1 milliamps. I know that going down this path, I have 4.63 milliamps. I know that going down this path, I have 5.32 milliamps. I know that the voltage from the top to the bottom is 0.25. So the voltage across here to here is 0.25. But remember, these two are in series. So across 54 was 0.25. So from here to here is 0.25 volts. I know that the voltage across both the 47 and the 27, so let me write that up here, from here to here is 0.75. And so what don't I know? Well, if we look at this 47 resistor, we know the current through it, and we know the voltage across it and the 27, but I don't know the voltage drop from here to here. And I don't know the voltage drop across the 27. The only other thing we don't know is I don't know the voltage drop across these 27s. I know across both of them it's 0.25, but I don't know it across each individual one. And so that's what we need to solve for. But since we know the current through the 47, remember again, V is equal to I times R. We can solve this. We've got 10.1 milliamps times 47 gives me 0.47 volts. So from here, 0.47 volts. And if we do the same thing for the 27, so I've got 10.1 e to the negative 3 times 27, I get 0.27 volts. Again, these should add up something close to 0.75, which they do, 74, close enough. Now we need to get these voltages here for the 27. So I've got 4.63 e to the negative 3, because it's milliamps, times 27. And I get 12.5 milliamps. No, what am I doing? 0.125 volts. So we get 0.125 volts. Again, they're the same resistor with the same current, so it's going to be the same if I do it on the calculator. Notice these are supposed to add up to 0.25, which they do, so everything looks perfect. Now we know literally every single current and every single resistance on this entire circuit. And so if I were to ask you, what is VR1? Well, VR1 right here is 0.47, 0.47 volts. VR2, well, it's 0.27 volts. R5 is the 27. So let me go to R3. Let's do it in order. They didn't even, look how nasty the book was. They didn't even put the resistors in order. So for R3, VR3, we had the 27. That's this one here. So it was 0.25 volts. VR4 is the 47, which is here. So it was, this was 0. I made a mistake on R3. No, I can't read my own handwriting. It's 0.125. So 0.125 volts. R4 was 0.25 volts. VR5, that's this 27, which is here, is 0.125 volts. If we were asked the current through R1 was 10.1 milliamps. It was the same through R2 because it's right here in series. So we got 10.1 milliamps. That's also the total. IR3 IR3, remember that's this one here. So our current is 4.63 milliamps. IR4, which is the one on this side. So that's this one, 5.32 milliamps. And finally, IR5, which was again on this one here on the left side, is 4.63 milliamps. And so we were able to solve every single voltage and current just by breaking it down and working our way back. All right, we'll try one more. I'm going to give I'm going to give you a pretty hard one, just so that we've covered everything from sort of simple ones like the last one to medium ones like this one to even difficult ones. All right, look at this one. They don't get much bigger than this. This is as hard as I'm ever going to make it. So let's look at this circuit and see what we want to solve for. So I want to break this down, and when we're done, we want to solve for all these values on the right. So notice we want to solve for every current through every resistor in this section. I want to solve for every voltage through every resistor at this section. And down here, notice I've labeled on this circuit different nodes. So this is point A, this is point B, this is point C, D, and E. I want to know what the voltage is at that point compared to ground. Notice we've got just the one subscript. And so you should actually pause it. Pause it and see if just what I've taught you so far, if you can solve this one on your own. I promise the answer will still be here when you get back. But let's see if we can go ahead and solve it. So pause it, figure it out. If you can't, come back and watch the video. If you can, for sure come back and watch the video. And I'm going to go ahead and solve it now. So again, remember, it looks horrible. It's an ugly problem. There's so much going on. But as long as we take it step by step, it's never going to be harder than collapsing two series or two parallel at a time. So again, if we look at this, we can see that we could actually choose to do series or parallel at first, because R2, this one here, and R3 are both in perfect series. And then we've got R4 and R5 down here that are in perfect parallel. I'm going to do the parallel first just to get it out of the way, because if I do those parallel, then I'll be able to do a couple series at the same time. But honestly, it makes no difference how you do it. So again, we're going to redraw, and it's going to take me a while because, like I said, this is a huge circuit. And so I'm going to go down here. We start, switch to my yellow, with 3 volts. After the 3 volts, we have to go through the 100. So I've got 100. After the 100, it breaks into the top and the bottom. And so I've got coming up this way. And again, I'm not going to collapse these two first. So I've got 47, and then it's another 47 right after it. 47. These are the two, the R4 and the R5, that I'm going to collapse right now. So if I come down the bottom, I'm going to collapse those two into one. And we've got 68 and 39 in parallel. So let's do that on our calculator. 68, 1 over x, plus 39, 1 over x, equals 1 over x. And we've got, I'm just going to call that 25.8. No, 24.8, right? I'm rounding it off right there. So 24.8. So we've got 24.8. After that, we have our 75. After that point, notice they come back together and they go to the ground. So they come back together. And then it goes to the ground. And I'm not going to draw the ground separate like they did. I'm just going to draw it like that. Alright, not so bad, right? Now we can see that we have 2 sets that are in series. And remember, we can't do series and parallel at the same time, but we can do 2 series at the same time. So I'm going to redraw it. So that's going to come down to here. So I've got 3 volts. I've got a 100. Then I've got my top one. and I've got the bottom two. I'm going to collapse. So at the top we have 47 and 47. I think it's going to be 94. 47 plus 47. We get 94. So I've got 94. And then we've got 24.8 plus 74. 74, 75. 75. And so we get 99.8. Okay. So I'll go ahead and close that circuit up. Now, we've got two that are in direct parallel. So I've got my 3 volts. We've got 100. I collapse those two in parallel. Goes down to 1 resistor just like that. And so we've got 94. I hate that keyboard thing. I'm sure you guys hate it more than I do, but 94 1 over x plus 99.8 1 over x equals 1 over x gives me 48.4. So I've got 48.4. Now we just have 2 in series. So again, I will collapse those two. Anybody know how to make that keyboard stop popping up? I'll give you extra credit. And then we've got those 2 in series. So we've got 100 plus 48.4 is 148.4 ohms. So now I know that was a huge, horribly ugly circuit, right? And if we tried to write an equation out for that whole thing, it would have been monstrous. It would have been horrible. But notice, if we break it up step by step, it really wasn't that bad. We just had to collapse a parallel or a series. Now we can't make it any smaller, so we need to solve for anything we don't know. Remembering our formulas, V is equal to I times R, or I is equal to V divided by R. It's the only formulas we'll ever have to use when we go back through this. So what I don't know here is I don't know the current. So we're going to have 3 volts divided by 148.4. That's going to give us, looks like 20.2 milliamps. Again, if we move it over by 3, so it's an engineering notation, 20.2 milliamps. And now we know every single voltage, every single current. So we're going to check this off and bring it up to here. So our total current is 20.2 milliamps. Remember, if I asked for total resistance, that would be this number, once we've broken it all down. So now what we don't know. Well, we brought back current, so it's probably a voltage, and it is. We don't know the voltage drop here, and we don't know the voltage drop here. So we use our voltage formula. So we've got 20.2 e to the negative 3 times 100. That gives me 2.02 volts for the first one. So we've got 2.02 volts for the first drop. For the second drop, we've got 20.2 e to the negative 3 times 48.4. And we get we'll call it 0.98. Look good to you? So we've got 0.98. And again, we should feel good about this, right? Why should we feel good about these numbers? Yeah, that's right. If we add this plus this, we get the total of 3 volts, which is exactly what it should be. So we know every current through every resistor and every voltage through every resistor. Check it off, move it back. So now I know the current here is 20.2 milliamps. I know the voltage across this one is 2.02. I know the voltage across both of these in parallel is 0.98. So what don't we know? And here's a little hint. It usually involves whatever you brought back. So notice here we brought back a current, and so we had to solve for voltage. The new thing that I brought back this time was a voltage, so it's probably current we need to solve for. So I know the current and the voltage across this one, so we're good here. I don't know the current here, and I don't know the current here. But I know the voltage and I know the resistance, so I can solve for it. So we've got 0.98 divided by 94 for the top one. That gives me 10.4 milliamps. So right here I have 10.4 milliamps. And for the bottom one, we have 0.98 divided by 99.8, which gives me 9.82 milliamps. So here we have 9.82 milliamps. Again, if we look at our work, quick check, I've got 10.4 plus 9.8. Yeah, that's something pretty close to 20.2. I'm feeling good. We know every voltage, we know every current. We're tackling this horrible, horrible problem. Now we check it off, bring back our new information. So now I know that we have 20.2 milliamps. I know from here to here, 2.02 volts. I know down this path, I have 10.4 milliamps. I know down this path, I have 9.82 milliamps. Now, I know across this whole set, right? Remember, this 94 and this 99.8 were both of these in series. And so I know from here to here what the voltage is, but I don't know what it is across these little tiny individual ones. So those voltages I need to solve for, and I need some more room to write. Let me see if I can move this over. Yoink. I don't know the voltage here to here, or here to here. And so we'll solve for those, again remembering that V is equal to I times R. And so if I do that, we've got 10.4 milliamps times 47. That's going to give me 0.49 volts for the first one. For this, oh, they're the same value, so it'll be the same for both of them. Again, if we add both of those up, it comes pretty close to our 98. Exactly our 98, but so it looks good. Now we need to get the bottom ones. So I've got 9.82 milliamps times 24.8, which gives me 0.24 volts for the first one. 0.24 volts for the first one. And for the second one, again we have 9.82 times 75. And we get 0.74. Again, those two added up equal to our 0.98. Everything looks good. We now know everything about this circuit. We've done it, y'all. We're back to the original. So now we've got, fill in what we know. We know the total current going this way is 20.2 milliamps. We know that the current going this way is 10.4 milliamps. We know the current going this way is 9.82. We know that across both of these up here, so I'm going to write it up here so I have room. From here to here, we have 0.49 volts. And here to here, we have 0.49 volts across R2 and R3. We know that across these two in parallel, the voltage is 0.24. So from here to here, we have 0.24. We know across the 75, we have 0.74. From here to here, we have 0.74. I'll write that again. So the only thing we don't know, what don't we know? Well, let's start filling out. Let's say it like we weren't sure what we didn't know. Do we know IR1, the current through this one? Yeah. IR1 is 20.2 milliamps. So 20.2 milliamps. Do we know IR2, this one? Yep. 10.4 milliamps. IR3, it's in series, so it has the same 10.4 milliamps. IR4, that's this one here. Do we know the current here? We don't actually know the current there, right? So that's one we're missing. We don't know that one, and we don't know the current here. But we know the voltage is 0.24, and we know the resistance. So I've got 0.24 divided by 68 gives me 3.52 milliamps. So 3.52 milliamps. So R4 is 3.52 milliamps. R6, which is, or R5, which is this one down here, the 39. We've got 0.24 divided by 39. So that's going to be 6.15. So we've got R5 is 6.15 milliamps. R6, right, that's this one. Notice that that's the same as this one, because this 9.82 splits up into a 3.52 and a 6.15, but it comes back together here. So we actually do know that one. It's 9.82 milliamps. If you forgot that, if you just did 0.74 divided by 75, you get the same thing, so it's okay. The voltage across R1, right? I forgot to write that, didn't I? I thought I wrote these voltages. The voltage across R1 is the 2.02. So from here to here, we had 2.02. So 2.02. Across R2, which is this one, we had 0.49. So 0.49. Across R3 was the same, 0.49. Across R4, which is this one, we had 0.24. And across R5 was the same, 0.24. And finally across R6, we had 0.74. So look at that, every voltage, every current through every resistor. Now it wants to know, what is the actual voltage at A? Well, remember, ground is 0 volts, and we go up by 3 volts, so A must be 3 volts. Well, what about B? Well, if we were at 3 volts here, and we drop by 2.02, then we just need to do 3 minus 2.02, because that's the drop. If we do that, we're going to get 0.98 volts for VB. VC is this spot. So if VB is at 0.98 and we go down by 0.49, what are we going to be at? Well, 0.98 minus 0.49 is 0.49. So VC is at 0.49. VD is over here. Remember, we're at this spot here, we're at 0.98 volts. To get to D, we have to drop by 0.24. So we have 0.98 minus 0.24, which gives me 0.74, which makes sense because we can see it on the other side. So 0.74 volts. And notice VE is actually ground, which is always 0 volts. That's it. We solved the most complicated circuit we could come up with for literally every voltage, every current, at points, everything. And so that's it. I know this looks scary, and I know it takes a long time, which is kind of annoying. We will have faster ways to solve circuits when we get to the very end of the course, but the math is going to be harder. So you have your choice, basically. You can do it quicker with much more difficult math, not much more difficult, but more difficult math, or you can take your time, step by step like this, break it down really easily, but it takes a long time. So if you have questions, remember, you know how to contact me. Just let me know, and that's it. This is the lecture for series parallel. You're going to have an exam. I promise if we have anything this complicated, it'll only be one like that. We might not have anything that complicated. We'll see. Talk to you soon.